Oh well. Okay. I'll find it later. Where'd it go? Where'd it go? Where'd it go? Okay. So definition of Ohm's law of equals IR. I would think that's an acceptable answer, but otherwise, if say he wants you to write out what the definition is, basically just turn this into words. So let's see. Ohm's law is the assertion that voltage and resistance, wait, not resistance, current have a, what is it, relationship that is, how do I write this? That is I guess you could say defined by R. Or you could say like the product of a circuit's resistance and current is proportional to the voltage. Any sort of way to express V equals IR in words should be acceptable. The next part says two 1.5 volt batteries are connected. That is not how I read that last time. If you connect the batteries in parallel on the circuit, what would be the total voltage? So it says two 1.5 volt batteries are connected in series to get a circuit at 3 volts. If you connect them in parallel, what would be the total voltage? Anybody have any guesses?
Isn't it 3 volts at the junction?
I want to say yes. As far as I know, it should be the same thing, so 3 volts. I looked this up earlier because I'm going to be honest, I wasn't sure what the answer was off the top of my head. But whenever I was reading, it said that two 1.5 volt batteries, whether it be connected in series or in parallel, is going to have a sum of 3 volts. I'm not 100% sure on the specifics of it, like if it's at a specific junction or if it's just of the circuit. But I think if you were to write the sum of your batteries would be the total voltage. Total. Three volts. I'm pretty sure that would be the answer. That's a little bit of guessing and knowing. The next part says a circuit has two batteries in it and several resistors in series and parallel combination. What rules can you use to analyze the circuit? So what rules did we use whenever we had a bunch of resistors in series and parallel and we had a bunch of batteries?
Kirchhoff's law?
Yes. Kirchhoff. Kirchhoff has like 3 different laws. There's like loop rule. There's, what is it? The total V in is total same as V out. There's, what is it? The junction rule, where same amount of current going into a junction is the same going out. So you use those 3 laws in order to analyze circuits with voltages and resistors. This one, admittedly, I don't know off the top of my head, so let me kind of speed a little bit. But does anybody else know?
Is it a voltage with a resistor? I think that's what he said in class.
I remember that was one method of turning because you can turn a galvanometer into a voltmeter and an ammeter. And I remember one of them, I think voltmeter, was you would attach a large resistance to it. But let me double check it just to be sure. Yeah. To use an analog meter, use a galvanometer, which is essentially a coil of wire with small resistance in a magnetic field with a pointer attached to that points to the scale. Current flow through the coil. Use the coil to rotate, and then use galvanometer. Okay, so I'm not 100% sure what he's expecting as an answer, but I would just kind of just describe the makeup of it. So a coil of wire with small resistance. Small resistance in a magnetic field. And then, I mean, I guess you can write what it's used for. So used to measure current or small amounts of current. In a circuit. I apologize for the penmanship. And then the next 2 parts just asks how to use a galvanometer as a volt. How do you convert a galvanometer to a voltmeter, and then how to convert a galvanometer to an ammeter. So I'm going to do this a little bit backwards in how I presented them. So to go from a galvanometer to a ammeter, a small resistance is placed parallel with the coil. You must use, I guess you put a small resistance. I just keep a resistor. And then for a voltmeter, you use, I think, just a large resistance. What is it, in series? Placed parallel. And then this one, large resistor. Place. A large resistance or resistor placed in series with the coil. So voltmeter in series, large, ammeter, small resistor in parallel. Okay. The next part is just SI units. Now, I don't know why I didn't put a line here. Resistance, I know that one, I know that one. Not 100% sure on that one. Not 100% sure on those two. Okay, so the first one is mu naught. What equation uses mu naught? Let me start with the two that I do know. So who remembers what resistance is?
Ohms?
Coulombs. No, not coulombs. Ohms. And then magnetic field. That would be the phenomenal car brand Tesla. As in Nikola Tesla, as in the future car of my dreams that I will never be able to afford. Now, mu naught, magnetic moment, and time constant. Mu naught. What do you use mu naught for? F is epsilon naught. Mu naught. I don't remember that one. Anybody remember where you use mu naught? This is a note because I also don't remember. Magnetic moment. If you can remember the equation, magnetic moment. I believe. Let's see. Tau equals P cross B. Newton, Tesla. Question mark? I'll circle back to those last ones, because I'm gonna be honest, I don't remember those off the top of my head. Nope, go back. Oh, it's not correct. Junction rule, loop rule. Does anybody remember what junction rule was? I think. Yeah. Okay. So junction rule, we have, I'll probably just write it, I in equals I out. At a junction, say I have so many currents going in and out of a junction. The sum of my currents going into the junction should be equivalent to the current going out. I'll probably just write it like this, I in equals I out. And if you want something more, just kind of write this in words like the current going into a junction is equivalent to the current going out. I apologize for my spelling abilities. I did not major in English. So loop rule, that one I don't remember as well. As junction rule. So if I'm not mistaken, it should either equal B or 0. 0. So loop rule, say you have a loop. Let me write it the other way. U1, R1, R2, R2. I make a loop. The sum of my currents within this, well, not, I guess not sum of current, I guess some of my voltages within this current should be equal to 0. So I don't know, I guess I would write that the sum of voltage in loop 1 should equal 0. And then as words, you can kind of just write the sum of the voltage in a given loop. That equals 0. And that pretty much sums up the concept portion minus the SI units. I'll have to look back at that. And then from here, let's go on to the harder part of the test, which is here. Actually, do I want to start with this one? Where's my little tutor sheet? It's not there. I'll start here. Determine what resistance is needed to convert a galvanometer into a voltmeter with a full-scale deflection of 10 volts. Your value of resistance should be a numerical answer. Sketch the labeled circuit, and that will show you how you would connect the resistor to the galvanometer. Now, minus the actual picture part, because I'm not really sure how I would draw a galvanometer, but I can at least help you all with the actual numerical part. So let's see, let's go back to white. The voltage, so we're going to use first Ohm's law, which is V equals IR. And we're solving for resistance. So where was I at? Wait, pen. I know that the voltage in my galvanometer is 10. And that's going to be equivalent to the current in my galvanometer times my resistance. So what we're going to do is one, I don't know if he expects you to guess this or he is supposed to give you values, but I kind of just did, if I was looking for resistance, I need I. So I just did an arbitrary like 1.5 milliamps. I would expect him to give you a value like this, but if not, I just kind of used an arbitrary value. Or he used this in his example. I actually started with I equals 1 milliamp. But my answer is still pretty close to his. So in his example, he used 1.5 milliamps. And then we're going to get 10 volts divided by my current. And it didn't give us a resistance, did it? Determine what resistance need to convert. Okay. So the resistance R is what we're adding. And then, so I guess R total. Now to be R, some resistance to add. And then most resistors come pretty low. I just use 60 ohms. I would say that's a pretty standard resistors. Obviously, they come much stronger and much weaker, but a pretty standard one is a 60 ohm resistor. So I went ahead and used that. So equals R plus 60 ohms. R equals 1.5 milliamps, or you could write that as times 10 to the negative 3 amps, and then minus 60 ohms. Whenever I was looking at the answers that he gave, whenever I was making this, he didn't actually give you the 60 or the 1.5. So I'm going to assume that he expects you to like make up a number if he were to give you a question like this. A standard, in theory, it really shouldn't matter what numbers you use. Whatever numbers that you use, just put them in this format and you're just going to get an arbitrary number. But if you were, I would expect him to give you like a current and a resistance. I think this was just a test that you know the actual how to use Ohm's law in order to figure out what resistance, and to know that the total resistance is going to be U with some resistance and then some resistance that you have to add in order to turn it from a galvanometer to a voltmeter. So at the end, you should get some, this is going to give you 6606. And then I got 0.7. I don't know where he got his answer, but using his numbers, I got 6.667 ohms. 6.606.7 ohms. He rounded kind of weird whenever I saw his answers. So that's that question. Fairly straightforward. The things that you kind of had to know that was just the physics was knowing they had to use Ohm's law in order to do it, and then knowing that the process of turning a galvanometer to a voltmeter was adding some resistance R to what you already had in your galvanometer, which I used 60. I'm not sure that's a standard for all of galvanometers, but I'm assuming that that's a fairly common one. So, not what I wanted to do. Image. Nope, go back. Done. Okay. Now this I took from the textbook. And whenever I was taking it, I forgot to actually put in the circuit. So I'll put that up right now. Okay. So R1, R2, R3, and R4 all are 10 ohms. And then the current going through this is 2 amps. And I want to know what is the voltage going, what is the voltage of the battery? So we have 2 resistors in series, and then in series to that, 2 resistors that are in parallel. So what I would do here, we have resistance, we have current, and I want to know voltage. So that is basically trying to scream to you to use Ohm's law. And it quite actually nicely gives you everything you need. So I is given. R is what's going to be kind of difficult, but if you know how to add up resistors, it shouldn't be too hard, especially in the given circuit. I would first start with your resistors that are in parallel. Does anybody remember how to add resistors that are in parallel?
Add them up in fraction format, like the resistance in the denominator, and then once you're done adding them up, you flip it around. Like flip the numerator and denominator.
So yeah, you take the reciprocals of all of your ones that are in parallel, and then you take the reciprocal of that. So you can do this another way if you're just highly math inclined and just able to see it. I wasn't able to whenever I took this class. It's also just the sum over the product. Either way, well, actually, product over sum. Because then you had to take the reciprocal of it. So if you're comfortable doing that, you can go straight to this. I personally still am not all that comfortable. So I start here. You're gonna get 1/, you're gonna get 2/5. I mean, 2/10, which is 1/5, which should be 20. No, it's not. 5. That's just some simple algebra. I did some of it in my head, but I think y'all can all do 1/10 plus 1/10. 2/10 is just reducing. The reciprocal of 1/5 is 5. I hope all of y'all can do that. The next part is, now that I have this resistor, so this just turns into 1 R34, which is 5 ohms. And now we have 3 resistors that are in series. So I trust that if y'all know how to do the sums in one variation, you'll know the other. So if you know how to do parallel, the series is just literally taking the sum of all your resistors. So R equivalent is R1 plus R2 plus, that's not a 2, that's an E, plus R34. You get 10 plus 10 plus 5. I trust all of y'all know how to add. Admittedly, I mess up every now and then, but I'm gonna hope that I know that this is 25. So now we have our R, and now they already gave us our current, so now it's just a matter of plugging in our values. So our voltage of our battery should equal 50 volts. Pretty straightforward. Admittedly, this is probably a pretty softball question in terms of what you can do with this chapter, but kind of testing your knowledge of, do you know how to add resistors, and do you know how to use Ohm's law? So there goes that. I'm going to do this a lot faster than I had hoped. Okay. So where's my phone? Start reading that here soon. Two parallel wires carry current coming out of the page with geometry as shown. Given I1 equals 2I2, what is vector B field at point P? Write your answer as a magnitude of B times the unit vector of the direction. For straight wire, the magnitude vector field can be taken as B equals mu naught I 2 pi r. Okay. There it is. So I admittedly kind of struggled with this for a while. Had to go back in the book and actually find some stuff. But we're gonna have 2 vectors stemming from these 2 wires. So where is it? We have current coming out of the page. Interesting. So if I'm not mistaken, obviously we're gonna have 2 vectors. So B total is gonna be B1 plus B2. And then is a matter of which one is which. So this, let's go to black again. Wire is going to exert a field or force, well, not field. I'll call that BA. B sub B and then B sub A. And then I'll just call these appropriately. B sub A, B sub B. Now, what is B sub A and B sub B? Well, B sub A, so it kind of gives you a lot of the answer in this part. So the magnetic field of B or A is going to be mu naught times the current of the wire. So that's going to be, where is it? I guess let's not use B and A. Let's use it 1 and 2. 2, 2, 1. I'm going to assume by size that this is going to be 1, 2. And then make sure I'm doing this right. B and then positive I. The I2 is in B negative A. So this one's going to be 2, 1. No, like 1, 2, 1. Negative A, which is that. And then 1 second. I'm confusing myself. B of 1 is in the B negative A, which makes sense. Okay. B1, 2 pi. I1, which makes sense. Actually, no. Why on earth did I copy it like that? There we go. Okay. Over 2 pi. Then I1. Move that over just a tad. And then we get the R, which should just be square root of A squared plus B squared. And then the unit vector. Hijo de la chingada. Okay. Unit vector. B I, yes. Minus AJ, yes. Okay. Fine. Okay. So vector 1. B is in the k hat direction. And then I. I swear I have dyslexia. Okay, B1. Obviously in the k hat direction. It's going to cross with my current. So this is where that cross comes in. So my k hat is going to cross with my this thing, the unit vector of my, I guess it would be current, which is going to be B minus A over the square, over the sum. If y'all taken calculus 3, and just should look fairly familiar, it's just your vector over your magnitude. And you do the exact same process for your B2. Mu naught over 2 pi, that's going to stay the same. I2, right? Yeah, I2. La 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 la. Okay. Oh, your R. Okay. Cross your BI plus AJ over A squared plus B squared. Now I'm going to move some of this down. So B1 is going to simplify to mu naught I over I2. Can I do that? Yeah, I think that'd be simpler. Let's see what is that for now. 2 pi. And then whenever you cross, you're going to get, let's see, I believe, let's see, the k hat's going this way. Should get positive just by right hand rule. Okay, yeah. By right hand rule, we're gonna get mu bi plus aj over the 2 square roots on the bottom. We're gonna multiply to get just regular a squared plus b squared. And then I guess from there I can substitute the I1 equals 2I2. So we're gonna get mu naught I guess 2 I 2 over 2 pi, I believe. Bi plus aj over a squared plus b squared. Same process, mu naught I2 over 2 pi. Whenever you cross, you're going to get bi minus a, no, other way around. No, other first time. Bi minus aj. Okay. Okay. Yeah. And then you get I think that should be it. Yeah. Doesn't really look right. B-I-H-A. Yeah. Yeah, okay. That should be right. And then you get B plus B1, B equals B1 plus B2. And then from there, it should just be simple addition, which is a lot easier than the first part of that question. So B equals la 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 la. I'm just going ahead and factor out this mu and I part. Mu I2 over 2 pi. And then we're going to get 2b plus b I hat. No. 2a minus a I hat plus 2b equals, I think, plus b j hat. All over a squared plus b squared. Then we're going to get b is equivalent to la 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 la. I mean, I guess probably could leave it like that, honestly. Can I simplify it? Other than just doing the, oh, you can do this. AI plus 3j over a squared plus b squared. That should be it. That's probably how I would leave it, yeah. I don't know that you can simplify it anymore.
Hey, for the j vector,
What time?
the 3b j. For the and the vector, would it be 3b j?
Oh yeah, sorry, 3bj, yeah.
I was just checking.
Whew. Gosh. This class is hard. I don't know why y'all are taking it. Okay. 705. Definitely don't have another worth of stuff to go through. Let's see. I have one more question, I believe. Let's see. Image. Oh, I have two more. And I didn't work these out. So that's going to be fun for me. Okay. So now is mode. Where is my pen? Okay. A rectangular coil of N turns in dimensions A and B carry a current I that is hinged along one long side on the y-axis. the coil is in the XY plane. The magnetic field B is directed at an angle theta. On the ZX plane, consider X horizontal, Y vertical. What is the torque acting on the coil about the hinge line? Okay, so the hinge line being on the Y-axis. And I want to know the torque acting on the coil about that. Okay, torque. If y'all remember from physics 1, torque is R cross F, but not from physics 1. F is no longer just force equals ma. Force is going to be let's see. We have current, we have length and height, and we have a B. So if I'm not mistaken, it says current I, and it says square, no, it says rectangle. It does not give me. Okay. So then I'll just call length times height. And I think, if I'm not mistaken, force will be current times the length cross my magnetic field. Let's work with that and see where that takes me. So let's see. And now it says it has n's amount of turns, so that's going to change this up a bit. So we're going to get n, however many n is, of this r cross f, r being, what is it, 2, I guess? I'm just leave it as r for now, cross I, L cross B. And that would be a vector 2. Okay. Now from here, what we're going to do is, it says B is in the what? The theta on the ZX plane. So that's down here. Hijo de la chingada. So my B exists down there. Well, let's see. Tau equivalent to n. This is on the ZX plane, and this is on the, I guess, X plane, question mark? R cross I, L cross. Down there, I'll call this theta. I think I'll call this theta. B sine theta K. Sine is opposite over hypotenuse, yeah. Sine K plus cosine theta J. No, I. Yeah. I. Okay. Okay. From here, let's see. What to do, what to do. Let's see, I have other way. BZ, and I have BX. Rectangular coil of N turns in dimensions A and B carry a current I. I wish this picture was a little bit better. Okay, so let's see my X component right here. No, that's not my X component. Sine zeta. X component 1, 2, 3, 4. My X component is only going to be on the, I guess, 1 and 3. And then my Z component is only going to be on the, well, they're perpendicular to all of them, so. And Bx is only perpendicular to 1 and 3. So Z will be on 1, 2, 3, and 4. And X will be on 1 and 3. So let's do this. Let's break this up. So 1, 2, 3, 4. Because we have 4 segments. Let's work that. So this first segment right here, I'm guessing that'll probably be this. It's going to be N R, and then R is going to be in the J, cross L, I, L, I, current is going in the I. I believe it'll be J, cross B, this should be the same. And that is going to be, let's see, that, let's see. R. 0, because my, let's see, LJ and then my 3 would be, no. Fine. 2, 4, and then 3. Let's just keep on working, and I think I'll figure it out. Okay. So these are all going to start with N anyway, so let's just start with that. Just realize that's not even a J. I cross Li. This one's going to be negative. Yeah. You're going to be negative again. And then you're going to be positive. And then cross all of these. B, and these should all stay the same. Yeah. Sine theta k plus cosine theta I. B sine theta k plus cosine theta I. B sine theta k plus cosine theta I. Okay. Yes. Complicated. Yeah, these are gonna be I, J. Cut. Gosh, this is confusing. 1, 2, 2, negative, positive, negative. Okay, yeah, that makes sense. That makes sense. That makes sense. The R's I'm a little stuck on. Oh, that makes sense because the R is 0 at. Okay, I think everything makes sense now. Okay, so now from here, it's just simple math. I, and then I have a K and an I. Yeah, so I and KI. And then cross that J. Okay, so I hope you're like good with the right hand rule. So mu2, so we're gonna have to move things around. Okay. 2 is gonna be, all the constants are gonna add together to multiply together. So we're gonna get N, R, L, I, B. We get I cross, no, let's start here. We get an I cross KB, which will give us I cross KI. And then that'll give us that. So negative J cross I cross negative J should give us K. Now, one more down here. No. Now, again, our constants should all come together. And then we have, let's see, we're at 3. We have, we have, let's see, J cross KI will give us J cross KI should give us a negative IK, and then cross that with I, we should get K again, I believe. No, this is the one that's hard. And God, this is not gonna be pretty. L-I-J. I'm at 3. I'm right here. My R is X. Not 100% sure. X, I, L, I. This one I'm a little lost on. But I think this is how it works. Because R is going to go into X because R is X. And then, forgot B. Cosine theta. J. Why is it cosine stay? B and sine. J. K. I. I'm not 100% sure why the cosine stays, but it stays. And then this last one should be pretty simple. It's just combine all of them. Using right-hand rule, you should deduce this. Because I, KI, this, and then you cross I with that, you're going to get negative. Okay. My lordy. And then you're still not done, because then you got to do total is equivalent to mu, the tau 1 plus tau 2 plus tau 3 plus tau 4. 1 is going to be 0. We know that because R is 0. My lordy. Okay. They all have an n in front, so we're going to factor that out. I'll just factor out everything. They have n, l, I, b.
Don't 2 and 4 just cancel or no?
2 and 4. Let's see. Yeah, they do. I didn't catch that yet. 2 and 4 will cancel. So you just get left with B. I mean 3. Yeah, because 1 is 0. Okay, so I'll drop the negative sign. 4 already canceled with 2. Wow, okay. So tau should just equal tau 4, I mean 3, which is negative n x l I. You can just simplify this to be bx. And then j hat. Okay. NXL IB. Yeah, I think yeah, okay. That was a mess. Kind of difficult. A lot of this is just how well do you know right-hand rule. So that's kind of how you're going to get through all of these cross products and your unit vectors. R, so it's just your distance between your origin and then out here. So from origin to out on your rectangle. On 3, it's going to be x because it's the same value. So that's neat. I is just a current going through. L would just be the length, and then your B is broken up into sine and cosines. Damn, this is a difficult question. And then let's see, I had one more question. Let's see if I can kind of get through it. Admittedly, I dislike this section with a passion. Okay. Consider the circuit shown. The capacitor C is completely uncharged at t equals 0 and begins charging as soon as the switch is closed. Assume R1 is equivalent to 2, 3, and R. The first part asks at time equals 0 when the switch is just closed. Is the circuit in the capacitor branch I3 0 or non-zero? Justify your answer mathematically and draw the resulting circuit. Determine the currents I1, 2, 3, and terms epsilon and R. Oh, my lordy. Okay. So, let's see if I can figure this out. Okay. 1, 2, and 3 are all R. Let's see. At time equals 0, the switch just closed. Let's see. That is a good question. I have this loop right here. Loop right here. And then, let's see, all of these are the same. So, let me see. Let's see. Hmm. When t equals 0 and the switch is just closed, the current of the capacitor, branch I3, 0 or non-zero. Justify your answer mathematically and draw the resulting current circuit. Determine I1, 2, 3 in terms of epsilon and R. Well, oh, okay. Well, I can answer the first part off the back. I3 is going to be non-zero. And that's because whenever you just close it, the capacitor is uncharged, so it works like a conducting wire. So we're going to get okay. And then we get I1. I'm going to, hijo de la chingada. I2, or I'm going to call that I3, and then I2. Okay, so that checks out. I can at least solve that first part. And then the next part, determine I1, 2, and 3 in terms of epsilon and R. So I should just be able to solve for the equivalent resistance. So R equivalent should just be R1, and then these two that are in parallel, that would be 1 over R2 plus 1 over R3, right, 1. That should give me, they're all R. So R times R over R plus R gives me R cubed over 2R. So I should get R equivalent is equivalent to R squared over 2. That's definitely a plus, not a oopsies. R plus R squared over 2R, R plus R over 2. That's 1 over 1, that's 2 over 2. We get 3R over 2. And then from Ohm's law, I should be able to do let's see. I1. So let's see. Did it give me V? It doesn't give me a V. So I'm gonna do this. I'm gonna do this. Yeah. Okay. So that's I1 at least. And then I1 is equivalent to I2 plus I3. And since R1 and R2 are equivalent, we can assume that I2 is going to be equivalent to I3. So I2 equals I3 equals I over 2, I1 over 2. So we get I2 equals I3 equals 2E over 3R all divided by 2, which would be E over 3R. Okay, that wasn't too bad. Took me a while to catch on, but I eventually got there. So at time, the biggest trick is that understanding at time 0, the C is basically going to turn into a wire. So we have basically no capacitor at time 0, and we just have a bunch of resistors and a battery. I know that for Ohm's law, that this battery is going to be equivalent to that first I, that I1, times the equivalent resistance. Rearranging it, we get I1 equals this, and we have it in terms of E and R, so that completely checks out. And then because of symmetry of R2 and R3 just so happening to be the same value of resistance, I can make this assumption that they're equal and therefore equal to the half of I1, which is quite nice. The next part asks after the switch is closed for a long time, so T approaching infinity, is the current in the capacitor in branch I3 0 or non-zero? And if I'm not mistaken, I think it's going to be 0. Let me double check just to be sure. Yeah, so I is going to be 0. Let's see. It's 2. I3 will be 0, and that's because the capacitor will be fully charged by now, and then the current in the capacitor will just be 0. So since Now we have this capacitor fully charged. This basically doesn't exist anymore. And we get the new circuit that looks like this. Which looks nicer, I hope. Let's see. So then we have I1 and then I2. So let's see. From Ohm's law, we get, let's see. I can probably I'll do it like this. E equals IR. So for this first one, let's just say I1 equals E over R1, which is just E over R. No, let's do it. No. Equivalent resistance. So E equals 2R, R plus R. This is equivalent to 2R. And then that should be equivalent to I2 because they have the same resistance. Equals I1. And then I3 equals 0. So on the numerical value of I3, I1, I2, and if I3 was 0, non-zero. And then after the switch is closed, where just 1T, I don't know why I put 2, is less than 5 tau, apply Kirchhoff's junction rule and loop rule to obtain 3 independent linear equations that allow determination of current I1, 2, and 3 as a function of time. Use loop 1 and 2. Okay. Last one, hopefully. So I know that T is less than, it said? Less than 5 tau. Let us see. I'm going to redraw this. Okay. Let's see. Okay. I have 2 loops. So at this node, we have I1 equivalent to I2 plus I3. That's just junction rule. And then loop 1, we should be getting, let's see. I assume I'm going this way. I'm going from a negative terminal to a positive terminal, which should be this negative E. And then plus R1 I1 plus R2 I2. which should be 0. And then for loop 2, I should be getting let's start with 2, so we get negative I2 R2 plus I3 R3, and then plus Q over C equals 0. Okay, I'm gonna turn loop 1 and loop 2 so that I have I's on one side. So loop 1 is going to be I1 plus I2 is equivalent to E over R. And then loop 2 is going to be, let's see, negative Q over C. No, let's write the I's first. We're gonna have, let's see, I3 minus I2 equals negative Q over C divided by R. Okay, so I know I have 3 equations, all in terms of I's. Okay. Would that just be it? After the switch, lesson 5 tau, apply Kirchhoffson to obtain 3 linear independent equations to allow the determination. So it would literally just be this. So it'd be I1 equals I2 plus I3. I1 plus I2 equals E over R. And then I3 minus I2 equals negative Q over RC. Three linearly independent equations, and then you can take the determinant. And then I'm guessing the next part, 4 and 5, you actually take the determinant and such. Okay, that wasn't the worst. And that's actually all I have. Let's see. Going back to these, let me see if I can just look these up really quick. Time constant. Yeah. I'm gonna assume it's not a second. Oh, duh. Hmm. Let me see. Let me just put it here. Time constant. It's RC. So that's ohms times C is, what is it? Time t tau equals RC. And then I believe C is in amperes. So is it A? But then you don't have. I don't know. I mean, off the top of my head, I can't think of those three. I'm not sure what those units are. I'm gonna go ahead and stop while I'm ahead. Do we still have everybody? Wow, y'all are still here. I'm shocked. So y'all's test is over chapters 9 through 9, 10, 11, I think 12 you said? 12. Let's see. 12, chapter 12, 11, 11. Yeah, so it looks like chapters 9 through 12. So that's current and resistance, direct current circuits, magnetic force and field, and then source of magnetic field. As you can tell, I think a lot of these questions involve Ohm's law in some sort of sense. So know how to use Ohm's law. I heard that y'all weren't able to go through Ampere's law today, so he told me to not include it. So I'm going to assume that if I told me not to include it, that he's not going to include it in the test. So everything from chapter 9 all the way to Ampere. It looks, I'm going to be honest, I hated this test the most, but I've talked to a lot of engineers and them say that this is their like more favorable test. So, I mean, if history comes to pass, I mean, hopefully a lot of y'all are gonna like this test a lot more than the first one. Y'all know what to expect now. Y'all did the first test. Use that knowledge going into this next one. If y'all have access to this review, I feel like the hardest ones are probably any of them that involve probably that magnetic field one that I really wasn't able to explain very well. So the one with the hinge, I think that one was really difficult. And then I think personally the Galvanometer one's kind of difficult. That's only because like I didn't learn that whenever I took this class. So okay, you said where's the review? So then did he not give y'all a review? I'll take that as a no. Well then I guess this was just for me then.
He gave us one. It's at the bottom of the modules page. It's titled Guidelines for Exam 2.
Okay. Was a lot of what I went over on that?
Yes, sir.
Okay, well then, yeah, that's exactly what he gave me to outline for this. I just honestly took a bunch of the questions because at least if I do them, y'all have some sort of idea about how some of them should go. I mean, unless y'all have any questions, I think if y'all just go through that, make sure you have all the answers. Y'all have the internet, you'll have your book, you have your online textbook. If y'all bought the book, you'll have that. Finish this, hopefully, preferably before Wednesday. If there's any of them that don't make sense, I know I didn't explain that hinge one very well. Hopefully you're able to keep up with the math. And if any of the ones that I didn't go over don't make sense, y'all can email me and I can explain it the best I can. Admittedly, I don't like circuits, so those types of questions I'm not very good at explaining, but I can explain the magnetism ones decently. A lot of it is just right-hand rule, magnetism is a cross product. That's how I honestly go through a lot of it. Other than that, if y'all don't have any questions, y'all are free to leave. I have nothing else to add, I don't think.